So if we're asking the question about whether those three vectors we started with were linearly independent, we may as well be asking the following question. Is it possible to find coefficients such that some linear combination of 1, 2 and negative 1, 1 actually equals the vector 4, 3? And at least according to what we're looking at here on this graph, on this diagram, it looks like it's the case that 2.5 times 1, 2 minus 1.7 times 1, 1 is, I'm just going to put approximately equal to here to cover our bases. It's approximately equal to 4, 3. But let's just assume that we've hit that on the nose. Exactly. Then what does this have to do with linear independence? In linear independence, we have a linear combination of all three of these vectors equaling the 0 vector on the right-hand side. How could I rearrange this equation to look like that instead? If I wanted a 0 vector over here on the right, what should I do? Let's just, subtract the 4, 3 from both sides. So I'll end up with here minus 4, 3. So 2.5 times the first vector minus 1.7 times the second vector minus 1 times the third vector is equal to the 0 vector. So if this is the case, then what can you tell me about the answer to the question, is 1, 2, negative 1, 1, and 4, 3 linearly independent? Yes or no? Why not?
Because the x's are all 0?
Exactly. What are the x's? What's playing the role of the x's here? 2.5, x2 is negative 1.7, and x3 equals negative 1 is a solution of the equation x1 times v1 plus x2 times v2 plus x3 times v3 equals 0. And what's important about this particular solution? Zach already said it. They're not all 0. So that's when he says, when the video says non-trivial, that's again what non-trivial means. Non-trivial means that these are not all 0. Because as was said in the video, it's easy to come up with some solution of this homogeneous equation, right? The equation with 0 on the right-hand side. Because we could just put 0 for all of our coefficients. 0 times 1, 2, plus 0 times negative 1, 1, plus 0 times 4, 3. That always works. But we call that trivial solution. Because it always works, it's not that interesting.
So, it doesn't work, it's not trivial.
So when there exists some other combination that works, then we call that non-trivial. Oops. There we go. So the trivial solution to this system always works. But whenever there is a non-trivial solution for x1, x2, and x3, so in our case, 2.5, negative 1.7, and negative 1, then we say that this set of vectors is not linearly independent. So linear independence happens when the only solution is the trivial solution. But if there exists some other solution which is not trivial, then this set of vectors is not linearly independent. Another common colloquial way to think about what this looks like, again looking back at our diagram, is that we were able to express one of these vectors as a linear combination of the others, is a linear combination of the others. And that's, I think, a powerful way to think about what linear independence means, is that I can get one of the vectors in my set by taking a linear combination of the other vectors in my set. That's kind of the notion of dependence in linear algebra, that one vector depends on the others if we can make that one vector from a combination of the others. So my 4, 3 here, my green point, which we can think of as a green vector if we like, just draw it in as a vector starting at the origin. But I can make this green vector via a linear combination of those two gray vectors. And therefore, this set of 3 is not linearly independent, because one of them depends on the others. I can make one of them through a linear combination of the other two. So using the definition, what do we have to show? If these vectors are linearly independent, or if they're linearly dependent, depends on the solutions to what equation? What equation do I really have to solve in order to answer this question?
Solve for the x's.
Say again?
Solve for the x's.
Right, to solve for the x's. But what are the x's? What role are the x's playing here? I have an x1 and an x2 and an x3. But how are those x's being put together into an equation? What are the x's being multiplied by, first of all?
Matrix of column vectors v1, v2.
Well, yeah, in the beginning, it's just the vectors themselves, right? x1 is the coefficient of my first vector, 1, 2, 3. x2 is the coefficient of my second vector, 4, 5, 6. And x3 is the coefficient of my third vector, 7, 8, 9. So the role of the x's is that they're the coefficients in this linear combination of these three vectors. So really our question is, how many solutions does this vector equation have?
Is it just unique or not?
Exactly. So that's the question. Is it unique? Or is it not unique? How come we don't have to ask the consistent question? How do we know that this system of equations is always consistent?
It's equal to 0.
Because what's equal to 0?
The 3 vectors.
Well, the three vectors themselves are not 0, but there exists a solution to this system always, no matter what. What solution always exists for this system of equations? The 0 solution, right. x1 equals 0, x2 equals 0, x3 equals 0. That's always a solution. Right? And so this system of equations is always consistent, so we don't have to worry about that part. Which means either we have one solution, or we have infinitely many solutions. Right? And which case is which? If I have only one solution, then are my vectors linearly independent, or are they linearly dependent?
Or it's unique.
If it's unique, if there's only a single solution to this system of equations, then independent. In other words, it's consistent because the 0 solution always works. Let me write that down here. The trivial, the so-called trivial solution, x1 equals x2 equals x3 equals 0, is always a solution. But if that solution is unique, then that means that only the trivial solution works, and therefore we would have independence. That's the definition of linearly independent. Is if the solution of this system is unique, then that means that only x1 equals 0, x2 equals 0, x3 equals 0 works. If the solution is not unique, then that must mean that there is some other set of numbers, x1, x2, x3, that make this linear combination equal to 0. And therefore, we would not have linear independence. So if we solve this system and find out that there's one and only one solution, then the set of vectors is linearly independent. But if we solve it and find out that there are infinitely many solutions, then the set is linearly dependent.
Which means one of those would be free.
That's right. Exactly. So we can rephrase this question about number of solutions, Jocelyn, as you say, to how many free variables are there. So let's do that too. So if our solution is unique, how many free variables are there? None, exactly. So there are no free variables if our solution is unique. Whereas if we have infinitely many solutions, then how many free variables we have? One or more, right. Say greater than or equal to 1 free variables. So now we know what we're looking for, right? We just need to figure out how many free variables there are in this system of equations. If there are no free variables, then the solution of this system is unique, and our set of vectors is linearly independent. But if there is any free variable at all, then the solution of this always consistent system of equations is not unique. Therefore, there exists some non-trivial combination of these three vectors that gives us the zero vector. And that makes this a dependent set. So now the table is set. How do we answer this question? How do we figure out how many free variables there are? Yeah, row reduction. Turn it into a matrix equation, augmented matrix equation, and reduce the rows. So the columns of my matrix, when I make this a matrix equation, are exactly the vectors at issue in the original question. 7, 8, 9. And then my right-hand side. There is a bit of a pattern in this one. It's an interesting question on whether or not that pattern generalizes. In other words, whether the answer that we get in this problem will also be the answer for other matrices that look like this. Actually, I remember investigating that question when I was a student at linear algebra the first time. It's a fun exercise. Because you can either do the inefficient way, which I did it, or there is an efficient way to do it as well. All right, so let's row reduce this matrix. Where is our first pivot in the process? Which number is our first pivot? Because all numbers are different.
1.
The 1. So our first pivot we're going to find up here. Now we just need to clear out everything underneath it. So what shall we do here?
Multiply the first row by 2.
Multiply the first row by 2.
Yep, and then subtract it from the second row.
Yep. That will get rid of this 2 here, make it a 0. And then 5 minus 2 times 4 will be negative 3. And 8 minus 2 times 7 will be negative 6. Luckily, having those zeros on the right-hand side means that nothing ever changes over there. So we're just going to leave those alone. Now we have the 0 in the second row. To get it in the third row, it's the same thing, just with 3 times the first row instead of 2. So now I'll have a 0 there. And then 6 minus 3 times 4 is negative 6. And 9 minus 3 times 7, 9 minus 21 is negative 12. And now our first pivot is by itself in its column. So we're done with that first column now. In the second column, where's my pivot? Negative 3. Because now it has a 0 to the left of it, which we need. And we just have to clear out the negative 6 underneath it. And how should we clear out the negative 6 underneath? Multiply the second row by 2. So 2 times the second row subtracted from the third, right? So that we're going to end up with negative 6 minus negative 6 gives me the 0 I wanted. Negative 12 minus 2 times negative 6. Uh-oh. Our entire last row has become 0. And so our search for pivots is over. So we have 2 pivots in our matrix. What's that mean? What do the pivots correspond to again? The pivot columns, let's say, correspond to? what are x1 and x2 according to this? What kind of variables, I guess, is my question. They're bound, right. That the values of x1 and x2 must be bound because they have pivots in their columns, which means we can solve for each of them in terms of the others. But what about x3? x3 is free. And that's what we really needed to know. Because what conclusion are we then able to make based on the fact that there is a free variable in this solution?
Question.
So what can we conclude here? Since we have a free variable, how many solutions does this homogeneous system have? Infinitely many. And so is this set of vectors linearly independent? No. Because there exists some linear combination of v1, v2, and v3 that gives us 0, which is not the trivial linear combination. In fact, we might well ask the question, well, what linear combination of v1, v2, and v3 gives me the 0 vector besides the trivial? In other words, what solution exists to this system besides 0, 0, 0? How could we find that? Yeah, let's just keep row reducing. So let's try and do this as quickly as we can here. Dividing the second row by -3, we're going to end up with 0, 1, 2, 0. And then clearing out the 4 that's above our pivot 1 there, we just have to subtract 4 times the second row from the first row. We'll make a 0 there. And then 7 minus 4 times 2 is going to give me -1. And there we go. Now we're in reduced row echelon form because every pivot is equal to 1 and is in a column by itself. So now to finish, we'll just rewrite these as equations. x1 minus x3 equals 0. x2 minus plus 2x3 equals 0. And then what do we say about x3? It's free. So we're just going to write x3 equals x3. And then rearrange the first two equations to get x1 and x2, the bound variables, by themselves in terms of x3, so their values are bound to the values of x3. x1 is equal to x3 when we move that to the right-hand side, and x2 is equal to minus 2x3. Then to get this into parametric vector form, we would just replace the x3s on the right-hand side by a new name. We would just call them t. Right? So if x3 is given the parameter value t, then x2 is equal to negative 2t, and x1 is equal to t. And so the parametric vector form of the solution set of this system of equations, write that up here in the upper right. That parametric vector solution is x1, x2, x3 as a vector is equal to t times the vector 1, negative 2, 1. And so for any value of t that I pick, I'm going to get a solution just by multiplying that t by the vector 1, negative 2, 1. So let's just pick an easy example. If I pick t equals 1, then I'm going to get a solution that x1, x2, x3 is equal to 1, negative 2, 1. And that's a non-trivial solution. It's not trivial because it's not the 0 vector. And you can check that if we take 1 times this first vector minus 2 times the second vector plus 1 times the third vector. We do indeed get 0, 0, 0. And so we have a linear dependence between these three vectors.